Good afternoon, everyone. I'm Sabine Hauert. I'm a lecturer in robotics at the University of Bristol, at the Bristol Robotics Laboratory in the Department of Engineering Mathematics. So I wanted to bring you on a journey, engineering swarms across scales. And I really think we have a common question, and that common question is, how do we make things work together? And you could apply that question to, how do you make 100,000 robots work in a warehouse? You could apply that to making 50,000 people evacuate a stadium, for example, and you could apply that to 1 million cars, robot cars, for example, that you need to have work together to bring people where they need to go. These types of problems are the ones that I try to solve as a swarm engineer, and I've been engineering swarms for the past 10 years or so. It's quite a challenging problem because very often you know what swarm or what group behavior you want to achieve, and as a swarm engineer, you need to figure out how to engineer the individual behaviors so that you get those desired group behaviors. You ultimately have your system work together. So the swarms that we've engineered over the years include swarms of flying robots. So I'm behind the camera here, and we could throw 10 of these flying robots in the air, and the goal ultimately was to create communication networks, for example, in disaster sites. So these 10 robots are networked through Wi-Fi, and they could connect to ground users and serve as a relay point. Since then, at the Bristol Robotics Laboratory, which is one of the biggest robot labs in Europe, actually, we've built a state-of-the-art infrastructure to really study how we can engineer swarm behaviors. So we have 1,000 of these little coin-sized robots, and that allows us to think about how you engineer swarm behaviors in huge numbers. And we also have these new robots, those white turrets. That's our teraflop swarm. And this is a swarm with fewer agents, but with GPUs on board, so that our robot swarm can start being a little bit more intelligent, learning and adapting as they go. So what can our swarms do? So when they work in large numbers, you'll notice they're very noisy. Here are about 100 of them moving randomly. But even with random motion, very simple interactions with their neighbors, they can quite rapidly, this is sped up, but they can quite rapidly create trails. And they can create trails if you have multiple objects. They can go around obstacles. So they can do a lot of things for free just through these emergent behaviors and properties of swarm intelligence. And so what could we do to bring these robots outside the lab and have them, for example, explore an outdoor environment? Here's 400 of our robots doing decision making. Here the right decision is blue versus red, so we want them to turn blue, which they ultimately do. Again, a lot of noise. We actually inject more noise into the system by having robots fail, so that we hope our swarm can come to the right conclusion, do the right thing at the right time, when we ultimately send them to do applications like environmental monitoring. And we're actually building an underwater swarm and a ground swarm just in the very early stages, so that ultimately we can take these rules and bring them to the outside world. Now, when you start playing around with these robots and you see that they work in the 1,000, you wonder what could work in larger numbers. And so we spent the past 5 years looking at the field of nanomedicine. So part of my team makes nanoparticles, and the idea is trillions of these nanoparticles, here in green you see actual nanoparticles, are quite impressive as vehicles to deliver drugs to tumors. And these particles work in those large numbers, and if we can understand their cooperative behavior, if we can make them work together, can they be more efficient in the treatment of cancer? And what you see here in red is an artificial tumor on a chip in some of our 3D printed microfluidic devices. So we're starting to see how these particles in artificial vessels can ultimately penetrate these tumors and distribute in the way we want them to distribute. So how do we do that? Well, the whole idea behind this is swarm engineering, and so it's very much a pipeline. And our pipeline starts from, what is that group behavior you're looking for, that swarm behavior. And then we need techniques to engineer the individual behaviors. So part of it is bioinspiration. If you look at birds and ants and bees, they actually have very interesting swarm behaviors that we can use, or using machine learning. So ultimately, we'd like to be able to click a button and use machine learning to automatically discover the individual behaviors that give us the desired swarm rules. And then, because we can't possibly wrap our head around what 1,000, 10,000, 1 million things are doing together, we need mathematical modeling and simulations to see that on a screen so that we can start to grasp at the complexity of these problems. And then ultimately, because we are an engineering department, we get our hands dirty. So we build the robots, we actually make these nanoparticles, and we look at what happens in the real world. Now this pipeline from complex problems to modeling is really the ethos of our department, which is engineering mathematics. If you still have a bit of time, I'd encourage you to go see their stand. And the complex problems that they're looking at range really across a huge variety of breadth, but things like cars and transportation, things like social networks, things like pedestrians working through the cities and the interactions that arise as a result of this big data. All right, so what I'd encourage you to all think about is what swarm challenges you need to have solved in your everyday life.